This is the voice of Sam Pickard, and I'd like to welcome you to my presentation. I'm really sorry I can't be with you in person. In fact, I couldn't really be much farther away, but more on that later. For now, I hope this goes some way to making up for it, and that 20-second slides don't make you seasick. Here we go. Okay, I'm part of the Low Carbon Technologies DTC, and my research focuses on generating low carbon electricity. It ranges from laboratory scale fundamentals to pilot scale combustion, and my interdisciplinary aspect analyses the development of carbon capture and storage, or CCS, as a technical innovation system. Too much to go on? Okay, here's some more detail. Burning fossil fuels releases carbon dioxide, CO2, into the atmosphere, while deforestation reduces the plant's ability to deal with it. A glut of these activities has led to increasing atmospheric CO2 concentrations, which is largely to blame for the increase in global average temperature and the changing of our climate. One of the leading sources of these emissions is electricity generation. In the UK, we still generate more than half of our electrical power from the unabated burning of fossil fuels. We must change our ways. The 2008 Climate Change Act mandates we cut our emissions across the board by 80% by 2050. A reduction of this magnitude is going to be a big task. This is particularly true for electricity generation, because as we move to things like electric cars and heating systems for our homes, the amount of electricity is forecast to increase, while the emissions from that process must fall. So how can we have more useful electricity while emitting less CO2? In short, there are many options, from renewables like wind and solar, to nuclear power, to reducing our demand and increasing system efficiencies. The problem is that our fossil fuel power industry represents over 100 years of investment and innovation, and that means we've got quite used to some of the benefits coal and gas can provide. Take flexibility, for example. The UK grid doesn't dictate when or how much energy we're allowed to use. To all intents and purposes, as much electricity as we want is available to us whenever we like. To respond to demand, the power plants need to be flexible, something nuclear power cannot offer. Or reliability. If we were connected to a European supergrid, we might be able to offset periods of low renewables generation with high generation elsewhere. However, at the moment the infrastructure isn't available, so to respond to demand we need plants that can be turned on, off, up and down very quickly, irrespective of what's happening around them. Symptomatic of our society, everything comes down to the price we're willing to pay. Thanks to a century of innovation and a price well below what the true cost of the fuel should be, fossil fuel power is still the cheapest way to get energy into our homes and businesses. So where do we go from here? Well, over the coming decades we must move towards a renewables-dominated, sustainable electricity system. But to get there we will continue to need fossil fuel plants. Fortunately, there are ways in which we can reduce the environmental impact of these plants. Two leading options are to replace some or all of the fossil fuel with a sustainable carbon-neutral option, or alternatively to capture the CO2 and permanently store it, preventing it escaping to the atmosphere. I look at combining these two technology options. Since biomass absorbs CO2 while it's growing, storing the CO2 produced from its combustion and preventing it returning to the atmosphere, it even leads to a process that is a net removal of atmospheric CO2, a very exciting prospect for fighting climate change. At laboratory scale, I'm interested in the types of changes we might expect if we swap new fuels and burn them in new combustion atmospheres, which make capturing the CO2 easier. For this work, I've reacted 5 fuels in 5 atmospheres and repeat each of these experiments at 2 heating rates. Each of the experiments is run in a thermogravimetric analyzer, which allows us to see how the reaction proceeds with increasing temperature, and from that, with some simple maths and assumptions, we can infer how the reactivity of each of the fuels changes. While looking at my results, I realised I had to modify the standard analysis procedure to correct for a bias which a lot of the literature seemed to gloss over. Hopefully my article on this will make it through the review process soon. As for the results, we found that increasing the oxygen concentration of the combustion atmosphere from 21 to 30% increased the reactivity of the fuels, and this was most pronounced during the final stages of the combustion process, when the char was reacting. CO2 to replicate an oxy-fuel system, one of the leading technologies proposed for capturing CO2 from power generation. These results showed a more complex effect, with some reactions occurring faster when CO2 was present, while others were slower. In short, though, we didn't see anything that should worry us about scaling up the tests. Alongside the laboratory scale, we also run some experiments in a small furnace that is scaled to represent what happens in a real power station. This allows us to test the fuels and combustion atmospheres and employ conventional combustion techniques like partitioning the oxygen in a furnace to reduce nitric oxide emissions. The furnace is about 4 meters high and produces about 5 to 10 times as much energy as your biggest gas hob on your cooker. The inside of the furnace is lined with a ceramic insulator, which allows the temperature inside to rise above 1300 degrees. With lots of instruments at various points, they can measure temperatures and the emissions of various gases in real time. We can change the fuel we use and the amount of biomass we blend with coal. The oxygen-containing gas used to burn the fuel, we can create a wide range of mixtures of oxygen, nitrogen and CO2, and inject different portions of these at different stages of the furnace. Okay, I can't go into everything in detail here, so I've picked out some results from the range of our data that look at emissions other than CO2. First up is biomass blending, then oxygen staging, and then combustion efficiency for air, solid boxes, and oxygen-enriched air, the hollow boxes, all of the fuels represented by different colours. The results show that, as well as reducing the net CO2 emissions from combustion, because an equivalent amount was absorbed during the growth phase, an increasing biomass fraction also reduces the sulfur dioxide emissions, with more sulfur trapped as a solid in the ash, as the scanning electron microscope pictures show. In conventional power plants, oxygen staging is used to reduce nitric oxide emissions and involves introducing some of the oxygen from combustion after the initial combustion reactions have occurred. From our results, we see this procedure is also successful with both biomass and in oxygen-enriched conditions. This graph shows how combustion efficiencies tend to fall as you increase oxygen staging when firing in air. But if you enrich the amount of oxygen in your stream, you can overcome this trade-off. This is important as it allows you to control for nitric oxide emissions without losing combustion efficiency and makes it easier to capture CO2. Moving away from the technical nitty-gritty, I also look at whether there are any other things which should hold back the rollout of this coupling of biomass and CCS. I completed this by analysing the UK CCS as a technical innovation system, and last year conducted an expert survey with 37 leading academics, industrialists and policymakers. From the survey results, we see the UK CCS adopts a similar shape to CCS in other leading countries. In particular, the survey highlighted that both the lack of a market for the technology to operate in and the lack of public awareness and support could hinder the development of the industry in the UK. The survey also asked for recommendations, and I have compared these with real activity in the past year to see how well the development of the industry is being managed. In short, the answer is quite positive, and with a few major exceptions, such as delays to demonstration projects and a still unclear market future, the policymakers have broadly speaking managed well. However, public perception and awareness of CCS is still very low, with the government refusing to engage the public, insisting it should be completed by project developers. At the moment, there aren't really any projects though, so the gap clearly exists. But it is impossible to discuss CCS without first thinking about energy in general. So during my time as an Ogden Fellow, I developed a lesson plan and asked the class to investigate the UK's energy future using the government's My 2050 Pathways tool, which shows that new technology and behaviour change are both needed to meet the 80% target. Teaching highlighted to me that most normal people aren't interested in power stations. So to get people interested enough to learn about CCS, I realised we had to make it fun. At the Green Man Festival, we built a carbon capture maze in which power stations find ping-pong balls of carbon, which participants had to capture and store to save the planet. You may remember I said that we need behaviour change alongside new technology for a sustainable future. Well, I'm trying to promote that too, and that's why I'm not with you today. And instead, I'm on a train somewhere between Vladivostok and Irkutsk, in the middle of Siberia, in the middle of winter. And I guess at about -25 5 degrees C. Why? Well, in order to get to the two conferences in Beijing and Kyoto, I decided that instead of flying to and from and emitting a chunk of CO2, I'd run an experiment to see whether it's better for the environment if I travelled by train or ferry instead. Alongside draft chapters of my thesis and a couple of papers, I'm writing a blog too. If you're interested, have a look. It'd be awesome to get to 2,000 views. So, to summarise, I combined engineering studies looking at biomass co-firing and carbon capture and storage with systems analysis to see whether this technology could reduce a chunk of UK CO2 emissions. I'm also passionate about energy-focused behavioural change and public engagement in this area. And that's about all I have time for. I'll happily take some questions if you can remember them from a few weeks. Thanks for listening, but for now, spasibo do widzenia.